Cart A, with a mass of 0.35 kilograms, moves along a horizontal frictionless track with a speed of 4.5 meters per second, and then hits and sticks to Cart B, mass of 1.6 kilograms, which is initially at rest. Cart B is connected to the end of a massless spring with the spring constant K is 75 newtons per meter, and it is stuck to the wall here. Calculate the momentum of Cart A before the collision. What is the kinetic energy of Cart A before the collision? And then find the initial speed of the two-cart system right after the collision and before they start compressing the spring. Then determine the kinetic energy of the two-cart system right after the collision. Is kinetic energy conserved during the collision? Explain. And what is the maximum displacement of the spring after the collision? What we're asking is how much does it compress? The momentum of Cart A before the collision is just its mass times its initial velocity, v0a, and we have that right up here. We always like to have our givens handy. Plug the numbers in and get 1.58 kilogram meters per second. Find the kinetic energy of Cart A before the collision. So now we use the kinetic energy equation, plug in the mass of Cart A, and then the velocity that we found on the previous slide. And remember, it's 1/2 mv squared. Make sure you square the velocity, and you get 3.54 joules. Find the initial speed of the two-cart system right after the collision. So Cart A hits and then sticks to Cart B, initially at rest. So that's a perfect inelastic collision. The phrase initial speed of the two-cart system right after the collision means the spring has not yet started acting on the block. It's not starting to try to keep it away, and the blocks are trying to push it in. So we're going to use the equation for the perfect inelastic collision as momentum is conserved. There's no external net force yet. The spring hasn't started acting on the blocks. Find the initial speed of the two-cart system right after the collision. Since we know that it's a perfect inelastic collision, we're going to jump right to the equation that's given for that. We have the initial momentum of each block equals the combined mass times the velocity of the two blocks stuck together. We eliminate this term. It's equal to 0 because block B is at rest. We then switch this equation around because we want to solve for VAB, so we put it on the left side, no big deal. Divide both sides by the combined mass, and here's our equation, which we've seen many times in the last few slides. Substitute our numbers in, and we get the velocity of AB is 0.258 meters per second. Determine the kinetic energy of the two-cart system right after the collision. Well, we found the velocity, of the two blocks right here on the previous slide, and kinetic energy is 1/2 mass v squared. So make sure you use the combined mass here, ma plus mb. Right here it is. That's a common mistake too. You might just put one of the masses in, and the other common mistake is forgetting to square the velocity. When you do that, the kinetic energy is 0.0649 joules. Is kinetic energy conserved during the collision? Well, very simply, no. Before the collision, this was our kinetic energy, and after it decreased all the way here to 0.649 joules. We actually expected that because kinetic energy is not conserved during a perfect inelastic collision, but it's nice that the math worked out. Where did that energy go? We didn't lose it, of course, but it was transformed into sound, some deformation of the carts, and heat. What is the maximum displacement of the spring after the collision? Well, there's no external forces acting on the system. You can say, well, what about the spring force? Well, that is part of our system. That's an internal force, so it doesn't count. The carts and the spring are on the same level surface, so we don't have to worry about GPE. At maximum displacement, that means the carts come to rest. So the only energy is elastic potential energy. There's no more kinetic energy. The carts have stopped moving. So the initial energy was all kinetic, and the final is all elastic potential. So we plug in our values. Kinetic energy is 1/2 total mass, ma plus mb, times the velocity squared of ab, and that equals 1/2 kx squared. Cancel out the 1/2s. Okay, they're on both sides, and we have kx squared is ma plus mb times v squared ab. We're solving for x squared, so we divide both sides by k, and we're over here now. But we want x, okay? So we take the square root of both sides. The only trick now is we have ma plus mb over k times v squared ab. We've got a square underneath the square root. Let's take it out, because the square root of a square is just the number, or the letter. So VAB comes out here, outside the radical. So if you do that, make sure you make it clear that it's outside the radical so you don't make any calculation errors. It's finally time to plug in the numbers. So we have our equation here, and remember we took VAB out. Why? Well, if we left it inside the square root, we would have squared it and then taken the square root of it. Why bother? Extra math work is always to be avoided. Put our numbers in, and we get the maximum displacement of the spring, or the amount it's compressed, is 0.416 meters.